Okie dokie.
So we're not saying any words right now?
We're not starting chapter 13 yet.
Okay.
So the Columbic potential. What does each variable represent? And be sure to include units. So we'll start with Mel. Pick a variable and tell me what it is.
It's Q.
Okay, what's a Q?
Coulombs.
Coulombs. Big C. Coulombs for what? What parameter? Charge. Right, so both of those be coulombs, I guess. Keep going, Jeffrey.
R radius.
Radius. Distance between what?
The two charges.
The two charges. Okay, there's a couple others, I guess, Kevin.
Pi.
Pi is pi, right? One left. Alyssa?
Epsilon.
Yeah, E0. What is that? Oh, you did, but it was a different epsilon. You learned this one, A equals EBC.
Oh, yeah.
But it's not molar extinction coefficient. No, it's not that. It's the permittivity of free space. It's a constant inside front cover of the book, or you just Google it. Oh, we didn't say what this whole thing is equal to, Gloriana.
The volume, velocity, the...
Big V.
I don't know. The Columbic potential.
Mm-hmm. What is it? We can kind of see. What are the units for permittivity of free space? It might be a real hint if you can figure out what the units are. E0. What's E0? It's per joule Coulomb squared per mole. So that E0, this will give you a real hint, maybe. That E0 has units of joules to the -1, Coulomb squared.
The coulombs is on bottom, so it's negative?
Well, the epsilon's on the bottom. So epsilon has units of per joule, Coulomb. So the Coulomb squared is going to cancel. The meter is going to cancel. You're just left with joules. So that means V must be... It could be work. It could be energy. I guess it depends on what's going on. But work pretty much means something's moving. This is a pretty static deal. This is the potential. This is like gravity. And we think of like gravity as potential energy. There's an equation for it. Does anyone know? mg h, right? And you get joules. All right, that's potential energy. This isn't gravitational potential energy. This is electric potential energy. So you have two charges, all right? So it's just joules. Okay. P is a function of R. This is written mathematically as, well, we don't even know what this represents. We don't really care. We're just going to do the math. At what value of R is P of R a maximum? Mel, what do you want to do? Set it equal to?
Zero.
Take the derivative with respect to R. Okay, so that can be a you-do. Oh, but do you see, it's not a straightforward one, Jeffrey. Help people out so they'll know what to do.
Oh, because the e to the negative.
Yeah, we've got an e to the r. Do you see the problem, Jeffrey? No? I see an r here, and I see an r here. Yeah, so how do we say the product rule in layman's terms there? Take the derivative of the first times the second, plus the derivative of the second times the first. So that's what you got to do. Okay, so see if we can come back and knock that out at the end if we have time. Okay, let's just see if we can get through these guys. What is the symbol for the principal quantum number when describing atomic orbitals? N. Kevin, what could N be?
1, 2, 3.
Yeah. 1, 2, like 1s, 2s, 3s. Remember all that? Alyssa, what is the symbol for the angular momentum quantum number when describing atomic orbitals? Principal was N, angular momentum quantum number. We kind of had this last chapter, in fact. It was that little L. What could it be, Gloriana? Goes all the way from something.
Plus or minus 1.
Negative L to L.
No,
That was Emsabel. Yeah, not there yet. It goes from 0 all the way up to something minus 1.
N minus 1.
N minus 1. There you go. Okay.
What would it be? 0 plus
0 to N minus 1.
2.
Oh, and what are the letters that correspond? So we should probably list these out. 0, 1. Little L. 0, 1, 2, 3, 4, 5. What's the letter? If little L is 0, the letter is going to be
S.
S. Then it went to P. Now, these are smaller case letters, right? P. And then D. F. Now it gets alphabetical. G, H, I, and just keeps going. Okay. What is the symbol for the magnetic quantum number? Look around Mel when describing atomic orbitals. We had the angular momentum quantum number. That was the length of the arrow. You can actually get the magnitude of the angular momentum from that. Then we had the magnetic quantum number. What was its symbol? We had it last chapter too. It's Emsabel. And that, what were its possible values? It went from negative L to positive L. Why do you think everything has this historical convention to it, but you really, remember you drew all these projections. You pick an L, you could draw all these projections, right? Because Emsabel H bar was the length on the what axis? The z-axis, this arbitrary axis. And it's not so arbitrary anymore if you flip on a what field? Magnetic field. So why not call it the magnetic quantum number then? Right? Because it finally makes some sense if you actually turn on the magnetic field. Fill in the blanks in the below table. Principal quantum number, only one value per box, and start with the value 1 and stop with 4. So let's just start here, I guess. 1. Allowed value of the angular, only one value per box. Okay, so next box. Allowed value of the angular momentum quantum number. Only one letter designation per box. So if n is 1, L is going to be 0. So L is 0, but they want us to write it as a letter designation. Yeah, pretty much 1s, right? List all the corresponding values of the magnetic quantum number. Yeah, just 0, because it goes from negative L to positive L, right? Total number of orbitals. Yeah, just 1. So we'll do this column last. Right? It says can't be completed until you do all the other columns. Let's just get you started on this. So now n is 1, we're done, right? Because L can't be anything else. Now n goes to 2. Now we can go, what's the first one we can write? So L's going to go from what to what? 0 to n minus 1. So we'll start with the 0, and we'll write what? Well, n is 2, though. 2s. And then all the corresponding values of, what could m sub L be?
1.
For this box right here, what's the L?
Oh, -2.
All right, this is talking about m sub L. What was the rule for m sub L? You didn't even care what n was. All you cared about is L.
So it's still 0.
So it's still 0. Because we said 2s. So you pretty much just look and see what you wrote. Okay. Keep going. There aren't any other m sub L's. N is 2. Now we could write 2p. Okay. What are the m sub L's now?
-1, 0, 1.
-1, 0, 1. Okay, again, do that last column last. Okay, can we keep going? Yeah, because there's no such thing as a 2D, right? That's too far. Okay, so now I gotta go to the next one. So n now is 3. Okay, so first one, 3s. Right? And what are the possible m sub L's? M sub L goes from -L to positive L, 0 to 0. Right, because S is just S. So 3s. Now the next one would be 3p. The one below that will be 3d. One below that will be
3s.
gotcha. See what happens when you drink? It just destroys it. See, okay, so you just fill out this table. All right, I think you can see how to do it. Now the idea of what you're going to want to do is total number of orbitals with the same principal quantum number. So over here, you just look and see, like right here, the number is going to correspond to these two boxes, right? And here, the 3's are going to be these boxes. So here I have what? 1, 2, 3, 4. 4, right? Here I have, well, you just count them all up. I think you should come up with 9, I think. Okay, and just keep doing that. So you do as a finish. And from the completed table above, it's not done yet, but what is the relation between the total number of orbitals and the principal quantum number? Do you see what's going on? N is 1, you got 1. N is 2, you got 4. N is 3, you got 9. N is 4, you're probably going to get 16. It's always n squared. Angular momentum is described by the quantum number, described by the equation, big L equals mvr. Show that L and h bar have the same units. Show that L and h bar both have units of angular momentum. And it should, because remember we said the z component of our angular momentum was just m sub L h bar, so h bar better have units of angular momentum. So, well, h bar you just pretty much look up. What is it, 6.626 times 10 to the negative 34? Joules per second or joules times second? Yeah, I thought it was joules times second. Okay, so we want to show that MVR has units of joules times seconds. That's all you really want to do. So M has units of?
Meters? Oh, what is it?
Yeah, what is M?
So kilograms?
Kilograms, because M is mass. V would be? And L equals MVR. What's V? What's V? It's a speed. It's actually it's a vector. So, but this is just magnitudes. We left the arrows off. So V is velocity. So that would be meters per second. And R would be meters. So equals question mark joules dot seconds. So you can finish that and show that the two are the same. That's another you do.
I just went there.
Okay, bye, Mal.
Bye.
The below diagram is a plot. I didn't know if I hit record, did I? Yeah, I did. The below diagram is a plot of atomic orbital energies versus atomic number. It'll be used to determine all electronic ground state configuration, electronic excited state configurations for this chapter. Again, we are going to use this chart to get all electronic ground state configurations and all electronic excited state configurations. Okay, what is that? Way back in Gen Chem, they said, write the electronic configuration for the calcium atom. Write the electron configuration for the sodium ion. Remember this?
Yes.
So the answer is always like 1s2, 2s2, that kind of stuff. Remember doing this? Okay. So what we did is we used the periodic tables, what we did. Do you remember this? This is how I did it. All right? And remember what was being filled? What was being filled right here? In this area. Yeah, I should go over the other one, shouldn't it? The S's. And in this area, this is the NS. The S's, just write S. The D's. And in here, the P's. Remember that? And that's what we use to write electron configurations. But there's things that are a little more involved, so we're going to use this plot. Okay? So let's see if we can use this plot instead of the periodic table. Periodic table will give you the answer, the right answer most of the time, but not always. So the ground state electron configuration of silicon. Okay. Silicon. What's the atomic number of silicon? Periodic table. What is it? 14. Silicon is 14. Okay, so you find 14 over here, I don't know, somewhere in the middle. Would be 14. And you just go up. So we need 14 electrons total. So first we're going to fill 1s. And then next we'll fill, according to that chart, 2s. And then 2p, then 3s. So let's put in some electrons because we're supposed to stop when we hit 14, right? But this is the idea. So 1s you can fit in 2, 2s, 2. Alyssa, 2p, 6, 3. Oh, what is that? 2. That's 10, 12. So in the 3p, I'll put 2 more. Done. Okay. An excited state electron configuration of silicon. Okay. So what we just did was the what state? Ground state. So how can you write an excited state? Well, let's rewrite our ground state. Just write the exact same thing. Okay, what would be an example of an excited state? Anybody know? Well, if we lose an electron, that's kind of like ionizing. So they don't want to ionize. They just want to get this thing into a higher energy state. So in other words, you got to stick with 14 electrons. You can't have any more or less.
I think we would move the 3s to the 3p.
Oh, that's a real easy one. Just pop one of these up into there. There's going to be a lot of possibilities. Right? You could promote one of these up to there, promote one of these up to there, right? Because the other ones are all full, so you can promote any of this stuff up into a 3p. That would work. Okay. You could also, what's next? I mean, those answers would work great. What's after 3p for silicon? 3p. Look careful. Look at 4. See here, it's going up. It's hitting 3D. So you could write here 3D 0, and in here, instead of writing a 0, just take one of these guys Okay. So all those would work. So I think you see the game that you're playing. All you're doing is finding the atomic number and making sure that you go up straight. And realize it gets tricky, especially for something like potassium. You see that? What gets filled first? If you're reading this right, for potassium, what gets filled first?
4s.
4s gets filled first, then 3d. So if you're, and potassium has how many electrons? 19. So anything with 19 electrons, you have to use, that potassium line. Make sense? What do you call it when you have two elements? For example, calcium has, where's calcium? Calcium has 20 electrons. If I say I have calcium plus 2, that means I really have not 20 anymore, but 18. Well, what has 18 electrons? Argon or neon? What noble gas? Argon does. Argon has 18 electrons. What were the words for that? Those two elements are isoelectronic. They have the same, what configuration? Electronic. They have the same electronic configuration. Two things that have the same electron configuration, they're isoelectronic. So that's really the word. Anything that has 14 electrons, anything that's isoelectronic with 14, you better follow that line. Right? For potassium, anything that has 19, potassium has 19. Anything that has 19 electrons, you better go straight up on potassium, follow potassium's line, 19.
So Z refers to the number of electrons?
Z is, well, the number of protons, which is the number of, so I'm just assuming neutral. So number of protons is the number of electrons. Yeah. And then we'll get into it more deeper later, right? Okay. But I see what you're saying. What if you have calcium plus 2? That has a different number of protons than, right? And all I'm really driving at right now is just reading this thing and realizing, for example, like for 19 electrons, 4s is filled before 3d. And getting these configurations. We're not worried about ions right now, and we'll play around with that later if it even gets that far. But you're right. I think if it was ions, I bet we should have followed the Z rule, not the electrons. But let's not worry about the ions. Oh, that's it. All right?
Can you go back and do that one problem?
Yeah.
Number 2?
So see if you can do this, and then we'll try it together. See how far you can get. And make your life easier. Do you see what I'm saying? If you're taking the derivative of this, that 4z cubed over a naught cubed goes right through the derivative, and you can just erase it because you have 0 on the other side. It's gone. So you don't even need to worry about this part. derivative of the first times the second sin f. There's the derivative of the first times the second plus the derivative of the second times the first. Right? So what can I do here? I can pull out a 2R and an exponential. You left with something like that?
Is that R divided by A naught?
I don't know. You tell me. Is that what it's supposed to be? Does the first line look right? The derivative of the first times the second plus derivative of the second times the first. Everybody agree with that one? Okay, then what I did is I pulled out 2r e to the negative 2r over a naught. Just pulled out what I could. So I'm left with 1, because I pulled that whole thing out. And then when I pull out the 2r, I'm left with a negative r over a naught, aren't I? Doesn't that look right to you? Gloriana, doesn't that look right?
That's what I got.
Doesn't that look right? So this whole, usually you get some number in this story, right? So how do you get zeros out of this? Well, what you got to do is you got to look and say, okay, well, one of these has to be 0. There's your possibilities. Either this equals 0, or this thing could be 0. So with the first one, how could you get this to be 0?
R equals 0.
There it is. Just make r be 0. So there's one answer. At what value of r is this a maximum? Well, one is r equals 0. Then the other one is
R equals negative a naught.
r equals negative a naught. If you set this expression equal to 0, what do you get? Because this equals 0, you bring a 1 over, you have a negative 1 on that side. Multiply it by a negative a0. Right. So r equals 0 is one answer. And here, isn't it just a naught? It's not negative a naught. I just see a naught. Get a naught? So that's the other answer. The negatives will cancel out on you. Okay. I don't know if we want to keep on going. Al might get upset. So good. I think you know how to do the rest of this stuff, right?